All right, the 4 laws of thermodynamics. So what does thermodynamics mean? Well, thermo deals with heat and dynamics deal with things that change. So we're talking about heat and changes. So let's get going with the first law. I'm going to use a website that I often find myself going to called Hyperphysics, and this is their page on the first law of thermodynamics. It says, the first law of thermodynamics is the application of the conservation of energy principle to heat and thermodynamic processes. So this equation right here, you don't need to know this equation for this quiz, the basic heat quiz, but what it says is energy equals heat minus work. So that is worth us writing down. So let's go back to my notes here, and it says the energy change, and I can't spell energy. The energy change equals heat minus work. Okay, so let's just go back really quickly and look at that. The first law makes use of the key and blah blah blah. Okay, we're fine here. Now let's look at this. What we're talking about here is we're talking about a system. Okay, so what's a system? A system is something. It could be you. It could be the planet. It could be the universe. So a system is I don't know if it's actually a place, but I think of it like a thing or a set of things that relate to each other. So you are a system, and you've got all of your parts, and the Earth is a system of which you are a part, but you can consider each one of these to be a system. So what if a system takes in some heat? So if some heat goes into a system, you stand by a bonfire or something. So if you take heat into a system, what's the energy change going to be? Well, it's going to go up. Your energy change is going to be positive. Okay? So what if you didn't have heat coming in? What if you went outside where it was really cold? So you're standing outside and heat is leaving you. So you are losing energy. So if the system of you is losing energy, then your energy change is going to be negative. Your energy is going to go down. Hoping that makes sense. Okay, this other part of the equation, work done. My favorite example for work done is to think about a car. And if you drive a car, what happens is it does work. It drives you around. So the car is doing work to the environment. It's driving up a hill. It's raising you up higher, giving you potential energy or kinetic energy, making you move. So when something does work, what's its energy change? Its energy change would be negative. And then another one, what about, let's say, we've got some kind of a wind-up toy, a little wind-up springy car, and we wind up the spring on the back of it, and we twist it around, and then the car takes off. Well, what we're doing here, when we added the energy, we twisted the spring, we were doing work to the spring. So when work is done to a system, in this case our system was the toy car. So if work is done to the system, then your energy change for that system is going to be positive. I'm hoping that makes sense. So that's the first law of thermodynamics. Now let's go look at the second law. Let's go to this tab right here. The second law of thermodynamics talks about the direction of heat flow. What's going on? How do you get work done out of a system? How does that happen? So the second law deals with heat or energy flow. Just as an example, I've heard people say before that cold travels places, and that's kind of a misconception. They think that cold can move. Well, it's true that you can move cold air or you can pick up an ice cube or something, but the thinking about it, the way people think about it is actually not correct. Heat always travels from someplace with a high temperature to a place with a low temperature. That's it. That's the simplicity of it. So a high temperature place is always going to be giving energy to a cold temperature place. If you happen to be watching this video in the winter, which is when my students usually get to this stuff, then outside of the building it is probably cold out, and inside the building it's probably warmer. No jokes about how cold my classroom is, okay? Anyway, right now then, heat is going through the walls and the ceiling. It's leaving the building and it's going outside. That's the way heat moves. So as time passes then, the temperature inside the building is going to go down, and you might not be able to measure it, but we're heating up the outside of the building. You know, we're heating up the air outside the building. The web page that we just took a peek at, one of the things it talked about was temperature. Another thing it talked about was potential energy. So the example they had was like if you had a cliff, and flowing over that cliff you had a river, and the water falls down. What you could do is you could put a device. Well, what am I doing? You could put a device right here, and as the water went by that device, it would spin, and we could use that to do work. So up here we had a high energy, and down here we have a low energy. And what do we use in the middle here? We use this device to extract work. We use that difference in energy to do work. So that's the big idea of the second law. Energy flows from a place of more energy to less energy, or higher temperature to lower temperature. The third law of thermodynamics, I don't think I have any quiz questions on this for this course, but just really briefly, the third law kind of serves to tell us where the minimum is. Maybe you've heard of something called absolute zero. This is a theoretical kind of a temperature where everything, all motion stops. Well, right now we think that that's not even possible because atoms intrinsically have a little bit of shake to them, so you can't ever get to absolute zero. But at absolute zero, everything in the universe could potentially be, the idea is that things could be really, really organized. There could be a low, something called entropy. Everything is more organized. But that's kind of beyond this class, and quite honestly, beyond me. Okay, so the zeroth law, what the heck is going on there? Why would you have a zeroth law? Well, the reason why is these other laws came first, and people, recognized how important they were, but then they thought of this other idea that these first two laws kind of had a weakness, and so they wrote the zeroth law that kind of should have gone here, but rather than rename these, they just said, well, we'll just call this the zeroth law. And it's kind of a commonsensical thing. Let's look at it. It talks about thermal equilibrium. So this example right here, let's say all three of these substances, A, B, and C, they're all touching each other. If A has the same temperature as B, and B has the same temperature as C, then that means that A has the same temperature as C. I know it sounds kind of silly, and the quiz question that I wrote for this is kids always get it right, but without this zeroth law, it's really hard to have a temperature scale that works. You have to have some kind of a logical setup to make your temperature differences to understand them. So there you go. So the zeroth law, I guess it kind of establishes temperature scales. Oops, temp scales. And that might not be the best way to say it, but I'm going to go with it. So there you go. There is your introduction to thermodynamics.